and also trying to find a better marker than this one prevents. I have some green. I only brought over a red and a green. I'm sorry, because I was not thinking ahead. I was thinking I need some extra colors for later, but I thought I had an extra black marker in there. Thanks, I already do have a green. Okay. So, first of all, if you don't know what topology is essentially the study of what you can get if you look at geometry where everything is allowed to sort of be pushed around, manipulated. We can sort of change its overall shape, but we can't cut it. We cannot glue parts of it together, or unless we do so in a controlled way. So the sort of classic joke about topologists is that we can't tell the difference between a coffee mug and a donut. The reason being for this, that if you take a coffee mug, right, you have sort of like the mug part, and then you typically have some kind of a handle on it. Well, if you take sort of the mug part and you shrink it down, you can kind of shrink it to where it is just a little piece over here and it turns into a donut, right? So this is the kind of thing that we study topologically. This would be different, though, than if I had something like this, where we have sort of two different loops that are tied together. This would be something that is distinct topologically from a donut or a coffee mug. Now, there's all kinds of interesting things that we can talk about in topology. In fact, we were just discussing some interesting ways in which topology comes up in chaos theory and things like that. But the part of topology that I specialize in is known as knot theory. And the study of this goes back quite a ways. The study of knot theory starts with the following question. If we have two loops in 3 dimensions, can we make them look alike without cutting them? And when most people think about knots, right, if you think about like tying your shoes into a knot or something like this, that is not topologically a knot. The reason being that these have endpoints. And therefore, if you work hard enough at it, you will eventually be able to untie it, because assuming that you can, manipulate the string sufficiently, the problem, of course, in reality, there's things like friction that's holding the knot in place. It can be very difficult to do this. But in theory, I can just take one end, find where it goes into the tangled mess. I can sort of pull that end through, and I can always make things simpler for myself as I go. So in that sense, that would not be considered a knot. The type of thing that we consider to be a knot is going to be an actual complete loop. So something that is topologically a circle. However, there are many different ways that you can have such a thing embedded in a 3-dimensional space, like standard Euclidean space, or typically for various reasons, we like to work actually in the 3-sphere, but it's equivalent to working in 3-dimensional Euclidean space. And so that's really our fundamental question. Are these two things the same topologically? Can we sort of manipulate one to look like another without having to cut it? Now, of course, if you're allowed to cut it, then you can make everything trivial. I like to say that Alexander the Great was the first knot theorist because he realized that the solution to untying a knot is to just cut it, right, with the Gordian knot. But if we're not allowed to take that kind of solution, then things get more complicated. So there's a really nice way to visualize these knots, which is known as knot diagrams. The concept of knot diagrams is not super old in mathematics, but it's been around in art for thousands of years in various cultures. And the idea here is this: if I have a loop, I can sort of lay it flat against the whiteboard here. Well, maybe not entirely flat. I can't necessarily flatten it out completely. If I could completely flatten it out, then it would just look something like this, and that's fine, but I may or may not actually be able to do that. But what I can do is I'm going to get a bunch of the strands, all the different pieces of this loop laying against here. And I can sort of, wherever I have part of those things going, I can draw an arc on the board. And in order to recover what this original knot looks like, all I need to do is to specify when two pieces are coming together at the same point, which one goes over the other and which one goes under. So what we do is we break one of them to show that this is the piece that goes behind this piece here. So if you think about two ropes here, like my fingers, this is the kind of three-dimensional image that you get from this two-dimensional diagram. And these are known as crossings. Now, for those of you who are in discrete math with me right now, really quickly, yeah, this is an example of a four-valent graph, and the information about the crossings is just labelings that we put at the ends of the edges, so you can regard these as an example of graphs as well. Now, you might recognize that some of these things show up in artwork a lot. An example that you might see that shows up a lot. Now, let's see if I can draw this. I always have trouble drawing this thing. Hey, I actually got it on the first try. Usually I end up having to go back and fix something every time I try to do this. So you might have seen this kind of symbol show up in like Irish manuscripts and things like that. All of these types of artworks, they used essentially knot diagrams. Like people just kind of intuitively knew that we can represent knotted up stuff by using these kinds of pictures. So the fundamental question that we asked at the beginning, can we make two knots look the same? We could ask, okay, if I have a knot whose diagram looks like this, would it ever be possible to sort of manipulate that loop of string in such a way that I could get it to just lie flat against the board like this? And by the way, if you can make a knot lie flat against the board like this, we call it the unknot, because it's effectively not really knotted at all. So the question that we want to address is this equivalent to the unknot? More generally, we might have lots of different knots that we're looking at, and we would like to know, are the knots that we're looking at equivalent to each other? So in trying to address this question, there is a set of moves on the knot diagrams that we can use due to a mathematician by the name of Reidemeister. And because of that, these are known as the Reidemeister moves on knot diagrams. And what he showed is that any manipulation that I do to the knot is going to have one of the following effects on the knot diagram. The first thing that we can do, which is not really a move, is we can just kind of move the diagram itself around, but not changing crossing. So like I could take, this loop here and I could say, well, maybe I wanted to actually go up and have this big bulge in it for whatever reason. But I'm just kind of sliding the pieces of the diagram around. I'm not changing the crossings. The Reidemeister moves themselves address the ways in which the crossings can change. So the first way that this could happen is you could take a strand and you could add a twist to it. So you end up with a little kink in your knot diagram like this. And there's a couple different ways you could do this, right? You could have it go this way, or you could have it go this way, or you can reflect it onto the other side. I'm not going to draw all of the different examples here because, there's a few different ways, but they're all equivalent under some kind of mirror images and things like that. So this is the first Reidemeister move. The second Reidemeister move says that if I have got two strands and they are next to each other in the sense that there's nothing between them, like this, then I can draw one strand over top of the other like so. So imagine you've got two ropes and you just pull the middle of one rope over the top of the other. That's what's coming up here. Again, you could do it the opposite way around as well. There's several different variations here that you can have. Okay, third possibility. This one is the most complicated. So this one essentially says the following. If I have three different strands that are all crossing each other like this, right? Then what I can do is I can take this top strand and I can move it across the other crossing that's right here. So what that's going to end up looking like is going to be this. Did I do that correctly? Yes, I did that correctly. Okay. So does everybody kind of see then what's going on here? I'm just taking this strand and I'm moving it across the other strand. Now, you might wonder how he actually proved this. I'm not going to give you all the technical details, but I am going to explain to you the essential way in which he proved this. And it's an idea that comes up in topology a lot called general position. So the idea behind general position is this. If you have a bunch of configurations of some object, there will often be sort of a generic way that those configurations can look. For example, suppose that I have a line in 3 dimensions and I sort of project it onto the board here. Well, for pretty much every line, that's going to project to a line on the whiteboard here. The exception will be if that line is perpendicular. But that's like the only way in which you can fail to do that. So we would say that a line in general position in 3 dimensions is going to project to a line on the whiteboard. There are very few exceptions. Well, similarly, what you can show is that if you have a loop in 3 dimensions and you project it to a knot diagram, then generically, in general position, the only things that you can get are going to be these types of crossings where 2 things cross over each other in the projection. You never get more than that. But what can happen as you move it around is you can show that there will be exceptions as you move it. And essentially, the 3 types of exceptions are going to be places where you end up with a sort of bird-looking thing in the projection, because what's actually happening here is you have your strand, and as you bring it into a kink, the tangent to this curve is going to be perpendicular to the whiteboard. So that's one thing that can happen, which is not generic, but which we can't guarantee won't happen as we move the thing around. And then for the second one, sort of the non-generic thing is that you can have 2 different parts of the diagram that just kiss each other like that. And the third thing that can happen is that your projection is going to have 3 different strands that all cross at the same point. And the way that you prove the Reidemeister moves is, first, you show that during a motion, these are the only things that can mess with the general position if your motion itself is in general position. Then you show that when you resolve this by perturbing the configuration just slightly in one direction or another, these are the different ways of resolving it. And this is how you can prove that the Reidemeister moves are a complete set of moves. So what I mean by a complete set of moves is that if 2 knots are equivalent to each other, so if I can manipulate them to look the same, then their diagrams will be equivalent under some sequence of Reidemeister moves and possibly just like shoving pieces of them around in the plane. So one of the ways in which this helps us is it kind of turns a problem in topology into a problem in combinatorics, because again, we can regard these knot diagrams as sort of combinatorial representations of these knots. And this is also how we are going to show that this knot that I drew over here cannot, in fact, ever be manipulated in such a way as to just lie flat in the plane. And the way that we are going to do this is, I kind of want to leave that drawn up there, but let me draw the unknot over here. This knot, by the way, is known in mathematics as the trefoil knot. You might see it in artwork. Sometimes people call it a Trinity knot and things like this. But we're going to see that these 2 are not equivalent to each other. You can never untie this thing and get it down to being the unknot. And the way that we are going to do this is using something called Fox tricoloring. Now, for some of you, after I show you what Fox tricoloring is, I'll kind of tell you also where this comes from, because it actually has a much deeper mathematical sort of foundation to it. But it's named after the mathematician Fox, who came up with this way of describing what happens with this particular thing. Now, the idea behind Fox tricoloring, this is an example of a knot invariant. And what is a knot invariant? Well, an invariant means that this is a property that doesn't change as we move a knot around. Which, by the way, the technical name for topologically moving a knot around is known as isotopy. So if you want to sound fancy about it, you can say that a knot invariant is a property that does not change under knot isotopy. And the reason that this is important is because if we have a knot invariant, and I look at two different knots, and I say, well, these things have different values for this particular invariant, then I know that they can't be equivalent. They cannot be related by isotopy or isotopic. We cannot manipulate them to look like each other. Because if we could, then they would have to share this property. So knot invariants provide us with a really good way to check whether two things aren't the same, but they don't necessarily provide us with a good way to check whether things are, because two knots could share a knot invariant, but not actually be the same knot. So what is the Fox tricoloring invariant? Well, the idea is this. In a knot diagram, we have the notion of arcs. An arc in a knot diagram is the portion from undercrossing to undercrossing. So this is easier to illustrate with a picture here than it is to try to describe in words. A lot of things in topology are easier to describe with a picture than to describe in words. So let's say that I have a strand over here and maybe another strand over here. And I have this, and then maybe this itself crosses over a bunch of stuff. Well, this thing here would be considered an arc, the part that I'm circling in green. Does that make sense to everybody? So in the diagram, each of the sort of connected parts of the drawing that I make are each considered an arc. And Fox tricoloring is the following. We say that a tricoloring of a knot diagram assigns one of three colors to each arc with the following condition. And this is really important because we don't want to just say, let's throw whatever colors we want onto whatever arcs we want. To be a valid tricoloring, what we want to have is the following. At every crossing, either all arcs are the same color, or all are different. There's one more condition, but I want to just draw the examples of this real quick to make sure that everybody understands this condition, and then we'll give the other part of the condition. So this would be valid. I could have all three. There's three arcs here, the one on the left, the one on the right, and the one that's doing the overcrossing here. All of them can be the same color. Another valid option would be that we have all three colors represented at this crossing. So that would also be valid. But this would be not valid. Does that make sense to everybody? So this is the kind of condition that I want. I either want to have everything be the same at the crossing or everything be different, but I don't want to have just two colors show up at a crossing and not a third. The other part of this condition.
Hey, Blake.
Oh yeah, sorry, what's up?
Just for people that are slightly colorblind, can you tell me the colors you put up there?
I'm sorry. So the one on the left is red, the one on the right is green, and the one in the middle is black.
Okay, what about the one below it then?
This is black, black, and red.
Okay, I got you.
I'm sorry. I know the colors don't necessarily show up that well, especially in this lighting. So yeah, I will try to be clear about that.
I'm an outlier.
No, you're totally fine. I'm sorry about that. I should have thought more about that. Would purple work better? I don't know if there's anything else that would work better, but
I can see it now that you tell me though.
Okay, yeah. So does everybody then see like what these conditions are and why what I mean when I say these two are valid and these are not? So the other thing that we do want to say is we want to say that we want to use all colors. I guess technically all three colors because we're only using three. So using all colors, later on we can talk about doing N colorings where we have more than three colorings. So this is why I'm used to just saying we want to use all the colors, but we're doing a tri-coloring, so we want to use all three colors. Now, here is the important theorem. Whether a knot diagram can be tri-colored does not change if we do a Reidemeister move. And this is going to take me a moment to write down. So why is this important? Well, this is important because if two knots are actually the same knot, if they are related by an isotopy, then their diagrams are related by Reidemeister moves. So what this theorem is actually telling me is that whether or not a knot's diagram can be tricolored doesn't depend upon which particular diagram I pick. For a given knot, you can either always tricolor the resulting diagram or never do it. And the proof, I'm not going to give you the full proof, but I will give you sort of the idea of the proof here. You just have to check all the possibilities with all of the Reidemeister moves. Actually, that's not totally true. I'll tell you a big shortcut later. It's also kind of a long cut because it requires a semester of algebraic topology, but I consider it a shortcut because I get to ignore combinatorics for the moment when I deal with it and say everything in terms of algebraic topology. So I like that better. But one way of proving this is you just check every single Reidemeister move and see what happens. As an example of checking this, supposing that I had, I'm just going to show you how to check the Reidemeister 2 move. I'll leave it for you to check the Reidemeister 1 and Reidemeister 3 moves, which are, well, the Reidemeister 1 is really easy. The Reidemeister 3 is really hard. I decided I would demonstrate with the one that's in the middle. There are really only two possibilities. The two curves could start with the same color, in which case, afterwards, we just leave all of these three resulting arcs the same color. So these are all black here. The other possibility is that they are different colors. So the one on the right here is going to be red, and let's say the one on the left is green. Then what's going to happen if I pull them over each other? Oh my gosh, I can't keep track of which pen is which color. What's going to happen when I pull one over the other here? Well, first of all, I'm going to have a lot of trouble drawing this. Let's draw that first. Then we're going to draw this part. I can get a valid tricoloring by taking this new arc that's introduced and making it black. So this one coming from the right is still red. The ones with their endpoints on the left are still green, but the one in the middle is black. And so if I already had a valid tricoloring in either of these cases, I still have a valid tricoloring afterwards. Again, checking R1 is really easy. Checking R3 is annoying just because there's so many different little arcs that you have to check. So there's a bunch of different possible options. But by checking all of these things, we see that this is in fact a knot invariant. So how do I know then that the trefoil knot is not equivalent to the unknot? Well, the unknot can't be tricolored because it's only got one arc and we need to use all three colors for a valid tricoloring. But the trefoil can be tricolored because I can take one of these arcs and I can make it red. And I can take another of these arcs and I can make it green. And I can leave the other one black, or whatever color we happen to be using for that third color. And this is tricolored. So this is tricolorable. The other one is not tricolorable. And therefore, the trefoil knot is not the unknot. So everybody okay with that? Anybody have any questions up to this point on this? Okay, so now let's get into a little bit of where does this actually come from? And so this is where I'm going to introduce a little bit more algebraic topology to you than we've been talking about so far. So there is this concept in algebraic topology called the fundamental group. Now, I'm not going to give you a huge, big description of the fundamental group on a technical level. I just kind of want to give you an idea of where it comes from. The technical details they're not super hard to work out, but they're complicated enough. I don't want to get bogged down on them at the moment. For those of you who are taking, how many of you are actually taking the abstract algebra course? Several of you, right? I know you're not, Dan. I thought you were taking abstract algebra. Are you taking rings and fields? Okay, but you've seen groups before, right? Yeah, okay. So just to remind you, a group is a set with a binary operation. It has an identity element. So when you multiply by the identity element, you get back whatever element you had to start with. Every element has an inverse. So you multiply an element by its inverse and you get back the identity element. And the binary operation has to be associative. So the idea behind the fundamental group is this. For any space, we can make a group technically, I should say that this space needs to have a base point where we are starting. And I'm going to illustrate this by not actually using a knot here. I'm going to illustrate this by using an annulus. So imagine that I've got an annulus like this, and maybe I pick my base point here. The way that we construct a fundamental group is this. We consider paths through space that start and end at the base point. And they can go through themselves and things like this, but they have to come back to the base point. And we consider these paths in the space up to what we call homotopy. Homotopy is a little bit like isotopy, except that I allow the path to be dragged through itself. So we don't think of the path as being like a string. We just think of it as like a path, basically. And so it can cross through itself over and over again. So as I move this thing around, it can cross through itself. In this case, for example, the loop that I just drew there, after I sort of get rid of this mess in the middle, you could see, well, this is actually just a loop that goes around the center of the annulus and comes right back, right? So we would think of those as equivalent because we can kind of straighten one out into the other. And so this is called homotopy. We want to consider paths up to homotopy. And to get the fundamental group, the group operation is concatenation of paths. So what this means is that if I have one loop that goes around and does who knows what, and then I have a second loop that goes around and does who knows what in this direction or whatever, I can form a loop by just saying, well, follow the first loop and then follow the second loop. That gives me a new loop. You got to check to make sure that all of this is okay so that it doesn't matter which representative we choose from the homotopy classes. And again, for those of you in discrete, this is an example of an equivalence relation and gives us a set of equivalence classes and things like that. So there's a little bit of technical stuff to check, and that's what I'm going to gloss over here. But it's not too hard to see that, like, if I can manipulate the first path in some way, then after I put the paths together, I can do the same kind of manipulation, right? So I still get the same homotopy equivalences. And it turns out that this does in fact form a group. The identity element is the path that literally just stands still. The inverse to a path is to just follow the path backwards. And to check that the operation is associative, just notice that, well, if you concatenate three paths, concatenation is an associative thing. So the fundamental group can be defined for any space. Now, in particular, what we can define for the not group is the following. For a not K, we consider the three-sphere. You can also just think of three-dimensional Euclidean space if you don't like thinking of the three-sphere, but we like thinking of the three-sphere because topologists like compact spaces. That's why we're obsessed with the three-sphere instead of working with three-dimensional Euclidean space. We take this and we cut the knot out of it. So essentially what you are doing is you are removing a tube around your loop of string. And then the not group is the fundamental group of the three-sphere with the knot cut out of it. And for an algebraic topologist, that's really all you need to say about it. But there actually is a lot more that we want to say about it as knot theorists in general. Because in particular, it turns out that there is a really nice way to calculate the fundamental group from a diagram of a knot. And this is the result of one of the most important theorems about fundamental groups called the Van Kampen theorem. But when you use the Van Kampen theorem, the way that you can calculate the group is this. We assign a letter called a generator to each arc. So if I have an arc in my diagram, and let's say that we have a crossing like this, I'm going to assign each one of these a letter. And then what we want to do is choose an orientation. So what that means is we're going to pick a direction around the knot that we're going to consider as like the forward direction, basically. And then what's going to happen is that at each crossing, we get a relation which says that, I got to make sure that I do this in the right order. Actually, there's different conventions for how you do this depending upon how you define the way that you write the group operation for concatenation. But in general, you're going to say that Z is equal to Y inverse XY. And then what is the resulting group? Well, the group is words in the letters that we've introduced up to equivalencies introduced by the relations. Now, obviously, there are more technical details that we need to go into here if you want to work with this in deep, really carefully. But this is the basic idea. The idea is like I could have a word that's like, you know, x times y times z inverse. Well, that would be a group element. But then what I would be allowed to do in this case is I would be allowed to say something like, well, I can replace z by this expression and get another word that I consider equivalent to this. And you can check that concatenating words is going to give you a group operation on this if you're allowed to cancel out whenever you have a letter times its inverse. So like this, I would be allowed to cancel out. And we consider a word with no letters to be the identity element, which we usually write as 1 so that we don't just have a blank space. It turns out that the resulting group that you get with these letters and the various relations that you're allowed to have, this is actually going to be the same group as you get from this fundamental group of the complement of the knot. So they're part of the 3-sphere that's left over when we cut out the knot. So this gives me a way to calculate the fundamental group from the knot diagram. Now, the way that this relates to Fox tricoloring, for those of you who know what homomorphisms are for groups, a tricoloring is actually a surjective homomorphism from the knot group to the symmetry group of the triangle. And it's just that, like, if you're trying to explain that to people who don't know what group theory is, that is going to sound confusing. But saying, hey, look, you put 3 colors and we want the, you know, everything has to be the same at the intersection, or they have to all 3 be different, that makes sense. And effectively, like what the tricoloring is doing is it's giving you a way to do a homomorphism from the knot group to the symmetry group of the triangle. So that's sort of where that is coming from. Okay, so that's sort of one of the basic invariants that you can have. Now, I'm going to really quickly go through some generalizations that we can deal with here, because this gets more into the area that I particularly focus on. One of the ways in which you can generalize knot theory is into what we call virtual knots. Virtual knots were introduced by a mathematician by the name of Kaufman, Louis Kaufman, and he introduced these as a combinatorial generalization of knots. So you remember that I said, like, a knot diagram can be thought of as a 4-valent graph, where we think of the crossings as the vertices, and then we've got some labels on these things. Well, one of the things about graphs is we can ask whether or not they are planar. In other words, can you draw them on a plane without the edges crossing each other? If we start with an actual knot and we get a diagram from it, then the answer is yes, the result will always be planar. But you could ask, what if we don't require the diagram to be planar? What if I am also allowed to have places where the arcs just kind of cross each other and we act like the crossing isn't there? And this leads to the notion of virtual knots. Now, you can define virtual knots purely combinatorially. There is a generalization of the Reidemeister moves to the virtual knots, but I actually prefer the geometric or topological interpretation of this. Topologically, this corresponds to knots in thickened surfaces where we can do surgery on the surfaces as long as it's to a part where the projection doesn't touch. And so how does that correspond to these virtual crossings? Well, the idea is this: if instead of having to draw this on the plane, if I'm allowed to draw this on any surface that I would like, then what I can do is I can say, I'm going to take this portion, going to leave this here, but I am going to glue a little tube out into 3 dimensions here. Like, think of connecting, sort of like, you know, take like a rubber hose or something like that and glue it to the whiteboard. And on that rubber hose, I'm going to be able to draw this part of the curve here, and now they're not going to be crossing each other. And so in this way, we end up with essentially a diagram on a surface. And we can think of that diagram as actually coming from a knot that is in a three-dimensional thickening of this surface. So this is one generalization that we can look at. Another generalization that we can look at is we can look at higher dimensions. So it turns out that if you have an object that is n-dimensional, it can be knotted in particularly interesting ways, let's say, because there's always exceptions here. It can be knotted in n+2 dimensions. So the easiest way to kind of think about this is to maybe think about surfaces in 4 dimensions. So how could these be knotted up? Well, one way to visualize this is just like with the knot diagrams, for surfaces in 4 dimensions, we have a type of diagram as well, and it is called a broken surface diagram. So the idea is you think of this surface in 4 dimensions, and you think about projecting it into 3 dimensions. Well, in 3 dimensions, what you will end up with is a surface, except the surface is going to potentially hit itself at certain points. And so what you do is you break the surface at those points. So maybe this is a sheet here, and then I have a sheet coming in here, and it keeps on going on the other side here, but I break the surface to show which part of the surface goes over which other, right? So this is like 2 walls that are meeting each other, but I've created a little gap in one of the walls to let the other through. And you can visualize this into 4 dimensions because essentially what's happening is to recreate the surface, you just glue in the strip between these, except you have to push it into the 4th dimension to get it around the surface that is here. That might seem really confusing if you haven't thought much about higher dimensions before, but once you really get the hang of it, it becomes pretty intuitive to be able to see that kind of thing. And just like with the Reidemeister moves for knot diagrams, it turns out that there's these things called the Roseman moves for these broken surface diagrams. So if 2 knotted surfaces are equivalent to each other by some kind of manipulation or isotopy, then their resulting broken surface diagrams are going to be equivalent to each other under some sequence of these Roseman moves. And you can actually generalize this up into arbitrarily high dimensions. It's just once you get past surfaces in 4 dimensions, the diagrams are such a pain to draw that it's not worth really doing, in part because you start having to draw them in higher dimensions to begin with. So it's really annoying. I don't know of anybody who bothers with the Roseman moves beyond surfaces knotted in 4 dimensions, if I'm being honest. And then what you can ask is, well, is it possible to generalize these higher dimensional knots to something like virtual knots? This is one of the things that I did in my PhD dissertation, is I was able to take the geometric notion that I described for virtual knots and show that you can bump that into as many dimensions as you would like, and you still get an invariant. Another thing that you can look at is you can then start asking, when you look at virtual knots, you can start asking, are there other invariants that you can define which might be better than, say, the fundamental group? And it turns out that, yes, there are various invariants that are going to be better than the fundamental group. One of those examples of an invariant is going to be something called the knot quandle. And by the way, the fundamental group still applies. We can do that for higher dimensions as well. And you can actually calculate it in exactly the same way. You assign a letter to every face of your projection, and then every crossing gives you a relation. It follows pretty much the same thing. So the knot quandle was originally introduced totally independently by Joyce and by Mateev who called it something else. He called it a distributive groupoid or something like this. I don't know how Joyce came up with the name quandle. I really have no idea where that's from, but I do work with these things a lot. A quandle is a little bit like a group if you forget about the group operation and just remember that you're allowed to conjugate things. So a quandle has a binary operation on it that is subject to the following conditions. We want it to have the property that, and many people such as myself like to write the operation as exponentiation because we use the exponentiation to represent conjugation a lot with groups, and that's essentially the way that the quandle thing behaves. We want everything operating on itself to be equal to itself. We want to say that x being operated on by y is invertible in y. And finally, we want the following really weird condition. X acted on by y being acted on by z needs to be equal to x acted on by z acted on by y acted on by z. This is called self-distributivity. So if you think of the distributive property for multiplication and addition, this is kind of the same thing, except it's the operation distributing over itself. And the way that you get these three conditions is you essentially just look at the knot diagrams and say, what would happen if I labeled every arc and then had some arbitrary operation at the crossings, and I require that the resulting algebraic structure be invariant under the Reidemeister rules. And you get the quandle. So this first condition corresponds to the fact that if I change from this to this arc here had better be the same as the original arc, but crossing under itself means that we're going to introduce, this one is going to be x acted on by x, and so it needs to be equal to itself. The invertibility corresponds to the second Reidemeister move, and self-distributivity corresponds to the third Reidemeister move. Interestingly enough, Joyce was able to show that the quandle is an almost complete knot invariant, which means that if two knots have the same quandle, they are pretty much the same knot. There is a small exception to this. They can be orientation reversed mirror images of each other, but there are only two possible knots that can have the same quandle. Now, unfortunately, that's not true once we extend this to virtual knots. For virtual knots, you can have different virtual knots that have the same quandle, no problem. In fact, you can have non-trivial virtual knots that have the same quandle as the unknot. For example, we have something called the virtual trefoil, which is a particularly annoying knot. Well, it's not actually that annoying, but it can be a little bit difficult to detect. And I'm going to do the easy way of drawing the virtual trefoil because I'm feeling a bit lazy about it. If we made this last crossing into, instead of a virtual crossing, if I made that into the same kind of crossing as we had up here, then we would get back something equivalent to the trefoil. But this is the virtual trefoil. And it's kind of difficult to distinguish this thing from the unknot. You have to use some other methods. So another thing in addition to the knot quandle, well, let me say this first. The knot quandle turns out to also have a topological interpretation. So just as the knot group can be interpreted as the fundamental group of this space, the knot quandle can be interpreted as a set of paths from a base point. So let's say that my knot is over here. This is my knot. This is some base point. You think of a little tube around the knot. And you think of paths that go from the base point to the tube. You allow the path to homotopy around, and you allow the end point to move around on the tube. The quandle operation corresponds to, if I have two different paths here that go to different parts, and yes, I realize this seems like a really convoluted definition, but it's actually extremely useful. The quandle operation corresponds to doing the following. You follow the first path out, then you go around the knot, then you go back, and then you follow the second path. And that gives you the quandle operation. So it turns out that the quandle has a topological interpretation. But you could then ask for virtual knots, because for classical knots, the quandle is pretty much good enough up to this mirror reversing thing. It is good enough for every knot, so we don't really need to go further than this. But for virtual knots, you could ask, is it possible to do an even better algebraic invariant? And the answer is yes, but there are some restrictions on this. This was also introduced by Kaufman. And he introduced this in a purely combinatorial way. So he introduced this idea of a biquandle. And the idea behind a biquandle is you take your knot diagram. Instead of labeling the arcs, you label what are called the semi-arcs. And the semi-arcs means that we also split things up when they move over another part of the diagram. So I would label 4 different things here instead of just 3 if I'm trying to use his biquandle idea. And then what he did is he just said, well, what algebraic structure could we get if we use words in all of these letters with operations corresponding to these crossings, and we require that this structure be invariant under the Reidemeister rules? And the answer is you get something that's kind of a mess. So I'm not going to bother writing down all of the rules because, like, it's frankly just a mess. But it is possible to work with combinatorially. Here's what's weird about it. Nobody can figure out, or nobody has figured out, topologically what on earth this thing is. So whereas the quandle, we actually have this like, oh, topologically, this is what's going on from it. For the biquandle, we have no idea. We have a combinatorial definition. We have absolutely no idea what the topological definition of this thing is. But I am working towards a possibility for this in the sense that I do actually finally know how to use topological techniques, classical algebraic topology techniques, to not get the actual knot biquandle itself, but to get colorings by certain biquandles. So these are just homomorphisms of biquandles. And to very briefly give you the idea of how you get these, and also how I was able to use classical algebraic topology techniques to get some results that previously required either biquandles or quantum invariance, which I haven't talked about today because we just don't have time to get into everything you can say about knot theory. The idea that I came up with, and this is something that I'm still working on extensively, is the idea of stacks. So the idea behind the stacks of virtual knots, right? I said before that you can think of a virtual knot as a knot in a thickened surface. And if you take a bunch of copies of that, you can glue sort of the bottom part of that thickened surface to the top part of another of this thickened surface, and you can end up with a bunch of copies of the virtual knot stacked on top of itself. In terms of the diagram, what's going to happen is instead of just having a crossing like this, you're going to have a crossing like that, and then underneath it, you're going to have another copy coming down here like this. And you can come up with some other variations as well. So for instance, you can also take a mirror reversal of some of these copies. There's all sorts of different variations that you can do from this. Now, this seems like a really weird thing to do because in classical knot theory, if we were not working with virtual knots, it would be useless. And here's why. For classical knots, we would end up with one copy of the knot on top of another. Well, I can just pull them apart. So it doesn't help me. For virtual knots, it does help me. Potentially surprisingly, like when I told somebody this, they were actually surprised that this ended up doing anything at all. And I fortunately had not thought that, oh, there was no good reason to try this because I ended up trying it and it ended up being really helpful. So one of the things that I was able to do with this is I was actually able to show that if you do this with a really difficult to detect knot called the Cuscino knot, actually there's a bunch of Cuscino knots, but these are very, very difficult to detect, meaning very difficult to show that they are not equivalent to the unknot. I was able to show that by using the stacks, you can use just the information from the knot group that you get as a result. It's technically a link group because it's got multiple components, but I haven't gotten into that yet. I was able to distinguish the Kashino knots, not just from the unknot, but also from each other using purely classical algebraic topology techniques. And the reason why I consider this to be particularly exciting is because this is something that you usually either need to use quantum invariance for, like the Jones polynomial, or you need to use biquantal stuff. And there are reasons, I haven't delved into this too deeply, but there are good reasons why from one of these stacks, what you can do is you can put some extra structure onto the resulting quandle. And when you put this extra structure, you get something that is a kind of a biquandle. And this defines, it's not the not biquandle, unfortunately. It's not that general. But it does define some kind of a biquandle, which is going to be the homomorphic image of the not biquandle. So it's not as good as the full not biquandle, but it does get us sort of a step closer to having a topological understanding of what the not biquandle is. And my hope is to be able to show that, first of all, there's interesting things about one of those biquandles that's actually reasonably computable. The other thing that I'm looking at is I sort of conjecture, I'm not sure if this is true, but I sort of conjecture that there's sort of like a, what is the categorical term here? Sort of like an infinite inverse limit that as you take the number of stacks towards infinity and you look at the resulting quandles and the structure that makes them a biquandle, that you approach the not biquandle itself in some way, which would be really cool because that would give us an actual topological interpretation of what is otherwise a purely combinatorial invariant that we don't really understand all that well and can't work with all that well. There are a number of other directions that you can go with this. I haven't even mentioned things like the welded knots, which is sort of a generalization of virtual knots where we allow some additional moves and that are very closely connected to knottings in higher dimensions. I also did a paper in which I generalized welded knots into arbitrary dimensions and talked about the resulting properties that we get. And you can extend like pretty much any classical algebraic topology invariance to all of those cases. I also haven't discussed things like braid theory, loop braids, and things like this. Yeah, so there's a ton of other stuff that you can do with knot theory and the associated kinds of topology that are involved. But I think we're coming down to the end of the time period here. So I'm going to end things there for the moment. Hopefully this has been enjoyable and taught you something new. And if anybody has any questions, I will be happy to try to answer them.
Any questions for our speaker? Well, if you have any questions, you can come up afterwards. But let's thank our speaker.
Thank you.